back, academics. Now, this is lesson one of rates of reactions. Now, here we're just going to be chopping up the introduction and the few things that you must know in terms of rates of reactions. Now, remember, here we're just going to start by understanding this word rate. Now, here, these will refer to the speed of something. So, how fast or slow. So I don't want to say a lot of words, but let's check how fast or slow something occurs. The rate at which something occurs, yeah, we'll be looking at that. This is just the speed of something. We know something can be fast or something can be slow. But here we are doing chemistry. So we understand that here we must speak about the rate of what? Of chemical reactions. Now, in real life, guys, you must understand some chemical reactions are quicker than others and some are slower than others. So to describe that, we use the rate of reactions topic to understand that some reactions take place faster and some reactions take place slower. But there are factors that will affect the rates of reaction, and I want us to go to those factors right now. Now, those factors that make the reaction to be faster or slower are these. Now, the first one, we don't want to say number one because you guys will think, yeah, number one is this one. No, we don't do it like that. So the first factor, right? So say factors, right, that affect the reaction rate, the reaction rate. Yeah, now understand one thing. Those factors, okay, that's not a line. All right, those factors, all of them, I'll give you a relationship will affect. The first factor that I want us to learn about is temperature. Right now, temperature affects a system. Now, in the temperature affecting the system, it will change the reaction rate, whether to be faster or to be slower. We will explore that part. Now, this is just a basic introduction. And then we have concentration. Now, there's something that you must understand. For concentration, we are speaking about substances in aqueous phase or in gaseous phase. That's what we're speaking about when we speak about concentration. So concentration only affects aqueous or gaseous phase. It won't affect solids. It won't affect solids or liquids. It doesn't do that, right? And you'll understand more of that when we do chemical equilibrium and why it does not affect the concentration. But for now, just know that for concentration, we only look at aqueous substances in aqueous phase or gaseous phase. Now, here we have another factor. Another factor is pressure, right? Here, pressure only affects gases. Now, you won't ever see me talking about pressure and then including aqueous things. Pressure will only affect gases. And how it affects gases or how it affects anything, we will come back to that one. Then we have another factor which they love a lot, surface area. We have surface area. Now understand one thing. Surface area will only affect any solids. Surface area will only affect solids. There's no time where we're ever going to speak about surface area affecting substances in aqueous phase. We don't do that, right? So please don't even think about it. Then we have another factor that, yeah, maning, but yeah, there's a few that they love. The first ones that I started with, yeah, they love those ones, and they also love this one. So they love this one where they say catalyst. Right now, a catalyst is a substance that will speed up the rates of the reaction by lowering the activation energy without itself getting used up in the process. So a catalyst will not get used up, right? A catalyst will not get used up. It does not change, basically, right? And let me say it will not get used up, but it won't change itself. It's just there to lower the activation energy. Now, what am I speaking about when I'm speaking about activation energy? Activation energy is the minimum energy required for a reaction to take place. So if this catalyst lowers that activation energy, it means that it will be reached faster, meaning the reaction will reach the activation energy much faster and it will take place much quicker. So that's simply what a catalyst does. But understand, a catalyst also is not, it's like temperature. It's not specified to affect a certain thing, right? And then we have the last one, which, yeah, I don't want to teach you this one, but we have to know it. The nature of reactants. Now, the nature of reactants can refer to a lot of things. Look at a few things, but it's a very simple stuff. This speaks about whether it's in lumps, granules, powder. It just tells us about the nature of what we are reacting. So if something is in powder, granules, whatever, we'll try to figure that one out, but I'll explain everything when we do it detailed, and then we start try to explaining each and every factor and how it affects the reaction rate. Now, these are the 6 factors that you need to know. And then the last thing that I want you to know in terms of these factors is that all the factors, let me say every, just say all the factors are directly proportional, write that down, directly proportional to the reaction. Why am I not writing reaction, guys? Reaction rate. What do I mean? I mean that, let's check, I change color over here so I can tell you something very quickly. Right? Now, all the factors are directly proportional to the reaction rate. Now, if we speak about something being directly proportional, we will speak about that in physics. If we speak about something being directly proportional, it means that if one increases, if we increase the factor, if we increase temperature, for example, it will increase the reaction rate. So if we increase a factor, just know that the reaction rate also increases. RR means reaction rate. Now, this means the same thing. If we decrease, because I don't want to just leave it there, if we decrease a factor, you must be able to understand that the reaction rate will also decrease. So the factors are directly proportional to the reaction rate. So every time when we increase the factors, we increase the reaction rate. We decrease the factor, we decrease the reaction rate. So, but we will explore that and how we even get to that. But you don't just say, I'll just explain and say, yeah, they are directly proportional. No, we don't do that. So we do explain this using something that you learned in grade 1 that we call the collision theory. Right, remember the collision theory. Now, you must understand that in order for particles, or not for particles, for a chemical reaction to occur between atoms or whatever that is reacting, they must collide. That is basically the word collision. It's all about colliding, right? Because not all reactions, not all things that you do not all things that you mix will react. Because sometimes that all the collisions that are there in that reaction are not enough. So just because you have collisions does not mean it will result in a reaction. A collision needs to meet certain criteria for it to make a reaction. So, for us to understand our reactions and the rates of reactions, we explain it using the collision theory. But this is one part. If you just understand, for particles to react, they must collide. But understand one thing, not all collisions lead to a reaction. Because if the collision does not meet the certain criteria that it's supposed to meet, there won't be any reaction taking place. And let's go ahead and explore that point right now, so I can just be able to show you what I'm talking about. I don't want to just say it, right? So in order, let me just say it here, right? In order for a reaction to occur, in order for a reaction to occur, let me say that, in order for a reaction to occur, this is what must happen in terms of what? Collisions. Because here we're speaking about the collision theory. So in order for a reaction to occur, there must be collisions, not just collisions. Because particles sometimes bounce off and then nothing happens. They just They collide, bounce off, nothing happens. But a collision that will do this will result in a reaction. A collision that is what? That is effective. Effective collisions must take place. You must know that. Effective collisions must be able to take place. But now understand one thing. You can't just say, hi, effective collisions. Hi, Bo. You don't do that. Effective collisions also have their own criteria. You can't just say, I'm an effective collision because I want to. No, we don't do that. It's an effective collision only if the particles collide. For the collision to be effective, the particles must collide. You must keep that. Must collide in the correct, which is another keyword, in the correct orientation. It's still a introduction. Don't try to grasp everything all at once. It won't happen. Don't do that to yourself. The particles must collide in the correct orientation. What do I mean? I mean that they must be in the same shape or same size, whatever, for them to result in an effective collision. Remember, everything that we're trying to do, we are trying to form an effective collision. Why? Because if we form an effective collision, that means we will be able to have a reaction. But for us to form effective collisions, the particles that are colliding must collide in the correct orientation. So if it's a triangle, it must collide with another triangle. If it's a square, it must collide with another square. It can't be a square and a triangle. It's not effective, right? So we do have ineffective collisions, and the ineffective collisions are the ones that do not lead to a reaction. But we don't need to know that, right? You don't need to know that. You just need to know what results in an effective collision. So they must collide in the correct orientation, and the key point that is loved the most is that the particles must collide, not must, but the particles must have sufficient, this one they love it, the sufficient kinetic energy. Now can I please use EK, right? They must have the sufficient EK to react. Now, Mamel, what am I speaking about when I'm speaking about sufficient EK? Let me just go and explain about sufficient EK. I said to you, for you to react, you need to meet a certain energy level for you to be able to react. But what is that energy level? That energy level is EA. EA ubani, activation energy. Right? Activation energy. Now, EA, if your energy or your kinetic energy of your particles is greater than this thing, there will be a reaction. If it's equal to this thing, there will still be a reaction. But if it's lesser than this thing, or the activation energy, it won't be any reaction. Why? Because this over here, guys, let me just give you the definition. This is the minimum energy. It's the minimum. You see, minimum means the lowest energy that you need for you to react. It's the minimum energy needed, which is very key, another keyword. You need this. Minimum energy needed to react. So now, you can see that the minimum energy required for a reaction to take place, it's fine. Still the right English, but I just want to make it easy so that I can be able to explain just now. What do I mean? I mean that if they say that there's a reaction over here, right, of particles over here, right, maybe certain particles over there, certain particles over there, and they tell you that not the kinetic, but the activation energy for this reaction is 5 joules. Right? Now you understand this is energy, it's measured in joules or kilojoules, is fine. Now understand another thing here. Check. This is just a brief explanation. I'm going to come back and just do everything again and again and again, because now I'm trying to explain so we can get you there, just to understand the basics. This is what, just that. Now understand, your EA is what? Is 5 joules, for example, right? It's hypothetical. Then when the kinetic energy of your particles, let's say your kinetic energy of your particles is 3 joules. Now if you check over here, your kinetic energy is lesser than the activation energy. So the energy that you have is actually lesser than the energy needed. Thus, over there, no reaction occurs. Now, you'll ask yourself, why does no reaction occur? Because there is no effective, I wanted to say this, effective collisions, because I just took you there. I said for a reaction to occur, there must be effective collisions. But you can't just say effective collisions. Effective collisions starts where? Starts from the correct orientation and the minimum having the sufficient kinetic energy to react. Now, in the sufficient kinetic energy is sugapi. If we come back to that same scenario, let's just go back there again. Let's say now in scenario number 2. In scenario number 2 now, this is what you have. This is what you have. Let's say, for example, let's take green. Right, let's say, for example, now the activation energy is still kept as of 5, which is a defender number, but you don't need to worry about that. EA, let's say, for example, is still kept at 5 joules. Now, let's say, for example, now your kinetic energy now of your particles, for example, is now 10 joules. If you check over here, your kinetic energy of your particles is greater than the activation energy. So you actually have the minimum energy required for the reaction to take place. If you have that, it means a reaction occurs. Why? Because there will be effective collisions. Because for an effective collision to take place, there must be sufficient kinetic energy of the particles for them to react. Sufficient just means enough energy to react, but not just enough. It must be the energy that is over the minimum energy that is needed for a reaction to take place. What is the minimum energy required? It is the activation energy. We call that the activation energy. For now, things might sound foreign. It's like, T1. Relax. Don't think about it too much. For now, things might sound foreign. Don't think about it too much. Yeah? But just understand one thing. If the more we collide, the faster the reaction rate. But again, another keynote, the more we collide effectively. So how do you say this? When I want you to say this every time, the number of effective collisions per unit time, as they increase, the rate of the reaction increases. But I'll just say this in plain English. So if we increase the number of effective collisions, but not just effective collisions, you must be able to say effective collisions per unit time. And I want this per unit time. I need that per unit time. If it's not there in an exam, but wrong, let's not go there. But for now, it's just an introduction. Let me not depress you. But the collision theory, you learned it in grade 1. No one is going back to that. But just understand that as you increase the number of effective collisions, what will happen is that the reaction rate will also increase. So if there are no effective collisions, there is no reaction rate, because there will be no reaction to begin with. So how can you measure the fastness or slowness of something that is not even there? So please keep that in mind, that we have these few things that we just learned about. Let's just consolidate on what we just talked about. Now, what we just talked about, so we can be able to understand what I was speaking about. So I can't just be preaching J, right? Check one thing. We spoke about the rate. The rate is how fast or slow something occurs in what? In a chemical reaction, because that's what we are all about right here. So that's what we are all about. Then here we learned that there's things that affect the reaction rate. And these are the 6 things that affect the reaction rate. We said temperature, which you can increase or decrease. And then we have concentration, which you can add or remove. Pressure, which you can but we'll talk about all those things. Surface area, we'll talk about those things. Now, catalyst, we'll talk about those things. Nature of reactants, but these are the factors that you must know which affect the reaction rate. But those factors, you must understand that all of those factors are directly proportional to the reaction rate. What do they do? So it means that if we increase the factor, the reaction rate also increases. If we decrease the factor, the reaction rate also decreases. So they follow each other directly. That's what directly proportional means. But we don't just explain that using general English, we use the collision theory. And the collision theory is a model that explains the reaction rates as a result of particles colliding with a certain minimum energy. That's the definition. They will never ask you that. Don't mind. They will never ask you that. But you need to know which we explain using the collision theory. But the collision theory explains to us, okay, in order for a reaction to occur, there must be collisions. But not just random collisions. Nope. There must be effective collisions. And that's the key word of the day. There must be effective collisions. If the collisions are not effective, there will be no reaction. But you must understand why are effective collisions important. You must understand that if a collision is effective, that means the particles must be colliding in the correct orientation, or the particles must have sufficient kinetic energy to react. And we spoke about this one. We said that sufficient, we just mean enough, but we just say that for it to happen, we need the kinetic energy of the particles to be greater or equal to the activation energy, right? You just need to know that. So if the kinetic energy is, if the activation energy needed is 5, you must have 5 or more in terms of your kinetic energy of your particles. That is the minimum energy required to react. What is the minimum energy required to react? That is the activation energy. It is the minimum energy required for a reaction to occur. So if the kinetic energy of your particles does not meet the required energy, it means there will be no reaction taking place. Why? Because we say that for a reaction to take place, there must be collisions. What type of collisions? Effective collisions. How do effective collisions occur? When particles collide with the correct orientation, or when particles have sufficient kinetic energy to react. Now check one thing. The particles may not have the sufficient kinetic energy to react, but they collide in the correct orientation. The reaction will still occur. So it just needs to meet one requirement. It just needs to meet. It's not like university where you'll get, they say maybe they want 7 for maths, and you get 7 for maths, and then maybe they say they want 7 for physics, then you get 5 for physics, then they don't take you. So in this one, you just only need to meet one requirement, which is, not the university style. They don't do that. So just need to know we have 2 requirements. For that. It's the correct orientation. Which is the first one. And then the second one is this one of sufficient kinetic energy to react. I don't know if I can fit it here, but sufficient EK to react. Here's the EK already there. Sufficient energy to react. So now just know that. So you need to understand the thing. This is just the basics. I wanted to take you through to this one, but we'll come back to explain everything one by one. Now understand that as the number of effective collisions per unit time. Why are we speaking about per unit time? I'm going to come back to why I'm speaking about per unit time. But in the per unit time, I need you to be able to see what I am talking about. But we have to include that per unit time. Jalo. Per unit time, always. Per unit time, always. Per unit time, always. Number of effective collisions per unit time. That means we'll also increase the reaction rate. But this means also if there's less effective collisions, it means the reaction, if there's less effective collisions, not Eastern Cape, effective collisions, that means the reaction rate will also decrease. So just know those few things, and I think that should be able to take you home. And then just grasp this, and I'll come back tomorrow, of course, to come back to the type of reactions. I don't want us to go to, there's a certain part where it will include type of reactions, 2 types of reactions, but we'll come back to that. And then if we just do that, it's just a basic revision of grade 10 and 11. Don't worry, it's not something new, right? But it's a basic revision of grade 10 and 11. And then if you just understand that part, just want to do a revision of that so that when I speak about it, you don't get confused on what is happening. But for now, just grasp this. Forget the calculations for now. It's coming. Don't worry. Just for now, let's grasp the knowledge, because I don't want to make this too long. Why? Because this is chemistry, guys. We explain, we consolidate. Don't cram. We explain, we consolidate. We explain, we consolidate. We explain, we consolidate. That's how we're going to be working up until we finish this topic of chemistry. I'll see you on the next one.